Good morning, grade 12, and welcome to another day of acid-base talk. First of all, I just have a little calendar here. I wanted to help keep the motivation going. So here we are on May 11th. I have a little 1 there. If we assumed we were going to, let's say, June 5th, I believe June 5th is when Nova Scotia finishes their classes. That just gives us 4 weeks. If we added another week for that, which is usually our exam week or assessment week, that gives us just 5 weeks. You can do this. You can hang in for 4 to 5 weeks. I know you can. Let's build up our background of acids and bases so that when we do get to post-secondary, it's going to be a lot easier for us. I notice the views on the videos are declining. Some of us teachers are talking and noticing that when the sun does come out, the students do tend to leave a little bit more of the schoolwork behind. Please try to stay focused, grade 12. I know you can do this. I know you can. I talked last week about how there were 3 definitions of acids and bases, the first being according to Arrhenius, the second Bronsted-Lowry, and the third being Lewis acids and Lewis bases. I had planned on going ahead with Bronsted-Lowry today. I decided no, instead we'll do a little bit more review on our KW, our KA, our KB. So please stay focused with me. I'm going to do a bit of review today for practice. You have worksheet 4 that you should have been working on. There's 14 questions on it. I did questions 1 through 8 with you, Wednesday's video and Friday's video. I'm going to finish it off today. On Saturday, you would have noticed that your most recent credit assignment was posted. So that's your 3rd credit assignment. It's going to be due this Friday, May 15th. And please, there's a handful of you that haven't done the second one. Get it done. A, don't procrastinate. That's a bad habit. And B, I want to post the solutions. I want to post my video explaining things. And I don't think it's fair to your classmates that I'm holding off until the assignments are in. Okay, so credit number 2 assignment was due last Wednesday. Get your tail feathers to get that done. All right, so here we go. Let's get going. Worksheet number 4, question number 9. It says, what is the ionization constant for the base hydrazine if a 0.5 molarity solution has the following concentrations? First of all, again, I'm trying to get you in the habit of writing out the equation that's going to help us on Wednesday and Friday when we move along with Bronsted-Lowry, etc. So we start with hydrazine because they're describing Kb. Without even looking at any table, I know they're talking about a base. Why is that important? Because when it's in water, it's going to lose its H from the water to form the hydroxide ion. That is what defines a base, the fact that there's hydroxide ions in that solution. So again, we have hydrazine being placed in water. Because the hydrazine is a base, it's going to take the H from the water molecule and form N2H5. And again, it's a positive charge because it's gained that extra H. Now, in keeping with the credit assignment that I've given you this week, I've asked you to write down your given, and I've asked you to identify what your unknown is. In this case, that's a rather large arrow. Let's try this again. Here we have 0.5 molarity. That is a given, and that is our weak base solution. Okay, and then we're given the concentrations of our ions. Now you'll note it has 0.5 here, but yet 0.499 here. That's because it has already taken into consideration that some of this hydrazine has broken down and formed these ions. So they're saying about 0.001 molarity has broken down and formed these ions. So when you go to write that into an expression, you have your Kb expression, which is your hydroxide ion squared, so your 2 products, over your reactant. And again, you'll see that they didn't use the 0.5. That's because they took into consideration that some of it has already broken down. So it started as 0.5 here, yes. Okay, that's where it started, but that's not what you have over here or here because some of that 0.5 is broken down. So it's no longer 0.5, but rather 0.499 because at equilibrium, it has lost about 0.001. And that's where we're getting those numbers. And remember, KB has no units. Okay, number 10, I thought number 10 was easy peasy. I'm giving you hydronium ion concentrations and you have to find the pH. The only thing to remember here is whatever number of sig figs your concentration has, that's the number of decimal places for your pH. And I'm just reminding you of the formula used to find pH. It's the negative log of the hydronium ion concentration. So there we go. You can just practice plugging those into your calculator and make sure that you do indeed have the same values. And I am totally and 100% embarrassed now because I'm realizing I didn't carry these to the proper number of significant figures. So isn't that awkward? So this should be 3.00, 6.000, and I want to take too much time away from our lesson to plug these in. Let me just see. If I have okay, so if I have 6.59 with an exponent of 10 negative, and I find the log of that, you know what? I think it will just be faster if I leave this for now, and when I post your notes, I will make sure I put in the correct answers for those. Anyway, the values are right, they just don't have enough number of decimal places, so that's extremely awkward, but I will fix that for you. Okay, now I've noticed some of you need a little bit of encouragement, okay? So this is the best I can do from afar. You can do this. There's only a series of formulas. I'm going to say without looking at your sheet, but the credit 3 assignment, I'm going to say there's maybe 6 or 7 formulas, and all you're doing is practicing rearranging those, rearranging those, rearranging those. The hardest thing is figuring out what you're given in the question and what you're looking for. So for your credit 3 assignment, I tried to help you with each and every question. I did far more than I would if we were meeting face to face. I wrote down little blanks that you can fill in for your given and your unknown, and it's going to make it easier to do this. Do not wait until Thursday to do the credit assignment, please. Start working on it ASAP. Reach out to me on Teams, and I can schedule one-on-one meetings, one-on-two meetings, whatever. Thursday, of course, is our extra help in the morning, but I can certainly meet you at any time, so just reach out on Teams for that. Okay, so for this question, just reminding you, it's the inverse log. So again, I think I did everything right here, which is sort of somewhat great. Nope, not this one. Okay, so there are 3 decimal places here, so I should have 3 significant figures. 3 decimal places here, so I should have 3 decimal places, so I should have 3 significant figures. Okay, this is awkward. Anyway, this slide is perfect, okay? So I put 10 to the negative 3, and this is my hydrogen ion concentration, or hydronium ion concentration, same thing. And again, I stress 3 decimal places in pH, and so I have 3 significant figures for hydrogen ion concentration. Okay, and same thing for this, 3 decimal places, 3 sig figs, 3 decimal places, 3 sig figs. 3 decimal places, 3 sig figs, 3 decimal places, 3 sig figs. Please practice punching those into your calculators, and know that if I asked you for POH, you could simply say that's equal to 14 minus whatever the pH was. So let's see what turned out over here. There we go. Oh, good, PJ. All right. So if I did ask you in future to find me the POH, you would just take 14, take away this 3, and that would give us the POH in this case, which would be 11.123. Okay. And some of you might have noticed as well, if I had asked you for the OH concentration, then, and I do ask this later on in this video, but if I gave you the H plus, the hydronium ion concentration, and I was asking you for the, come on, Tate, there we go, OH concentration, you would just take your Kw, which is 1 times 10 to the negative 14, and you would divide it by, there we go, your 1.00 times 10 to the negative 3, which is your hydronium ion concentration. Okay, so just showing you here how you can go back and forth between the two. So again, if you're given pH, you can find pOH by just subtracting the pH from 14. If you're given the hydrogen ion concentration and you're looking for the hydroxide ion concentration, you can just take Kw and divide by the hydrogen ion concentration. Okay? Okay, ionization constant for acetic acid is, find the percent ionization. Okay, first of all, I want you to notice that this is acetic acid. There's the formula. If you didn't know what the formula was, you could look on your table of acids and bases. Okay, and I also want you to note that the Ka is less than 10 to the negative 4, so we don't have to worry about an ice table. We don't have to worry about that little bit of acetic acid that's breaking down. So there's our acetic acid. We place it in water. Because it's acidic, we know that it's actually going to give up one of its H's. It's not going to take an H from water, but rather it's going to give an H. So we end up with hydronium, and the acetic acid becomes the acetate ion. Now, because it's such a weak acid, 1.76 times 10 to the negative 5 is a small Ka. Not very much of this is going to break apart, okay? So we have a double-edged arrow here, but what we're trying to do is figure out what percentage, and it's not going to be very much because it's a weak acid. So what do we know? We know the Ka, and we know the concentration of the acid. So if I were asking you to do this as part of your credit assignment this week, I would have said, okay, what do you know? You know the Ka, okay? And, okay, anyway, you know the Ka. And you also know the concentration of the acid. So you would look at your green sheet and you think, okay, what formula do I have that connects Ka, and concentration of acid? And you would have found this formula, Ka and concentration of acid. When you rearrange that, you can find your H plus. Okay? Now, I'm going to get rid of this little part because I don't want that to throw you right now. So I'm going to cover that up. Anyway, so there's the formula you would have found, or the equation you would have found. You could have rearranged and solved for H plus, which is great. Great, thanks Tate, you found H plus, except we're looking for percent ionization. So then you would have looked on your green sheet and you would have found a formula for percent ionization, where you plug the H plus over the concentration of the acid and times it by 100. Now you'll see you get a small percentage. That makes sense because acetic acid is a weak acid, so its percent ionization is going to be small. Okay. Now, I wanted to point this out. If I had asked in the question for pH as well, if I had added a little blurb up here, in order to find pH, you would have just taken this hydrogen ion concentration and you would have plugged it into your negative log equation. So you would have had a pH of 2.726. And again, 3 significant figures, so that's why 3 decimal places there. Okay, for question 13, couple of things. First of all, HA ionizes 2%. Because it's 2%, again, we know it's a very, very weak acid, not very strong. We don't know what acid it is, it's called HA. HA is no particular acid, it's a generic formula. So I've written out the generic dissociation equation here. And again, because it's an acid, the H blue is lost from the acid, moves over to the water and forms hydronium ion. Okay? So what are we given in the question? We're given the concentration of the acid and we're given its percent ionization. So again, we don't know what the acid is, so we don't know the Ka. We can't look it up on any table. The 2% ionized isn't very strong. So we could have left out the 0.02, and I'll show you what I'm talking about over here. We have the concentration of acid and we have a percent ionization. We know to use this formula. Percent ionization we have, and concentration of acid we have. So we can rearrange to get our H plus. Okay, so that's the 0.02 for the H plus, the hydronium over here. Now, if we're looking for Ka, once we have that H plus, we can use this formula. Okay, now the Ka is equal to the H plus 0.02 and the concentration of the acid. Now, initially, the acid was 1 molarity, but it broke down. Okay, that 1 molarity broke apart. Now, I'm going to leave the concentration over here. I'm not. Let me come back to this. Okay, so let me rephrase. We have a solution of 1 molarity, and then it goes in water. Some of it breaks apart, so it's no longer 1 molarity. Some of it breaks apart and forms the hydronium and the acetate. Okay, now you've already told me up here, this is how much H plus forms. So what that means is the acid that started at 1 molarity is actually 1 less the hydrogen ion, okay, because that's how much is broken apart. So that's where we get the HA on the bottom, okay? Now, because it's a weak acid, and you know that because it's only 2%, I am okay with you leaving out this 0.02. It's not very much. You leave that 0.02 out, that's what I've got under here. If you ignore the little part that it's broken apart, you still get a Ka of 4 times 10 to the negative 4, and that's very close, okay? So most times we don't worry about how much has broken up. So we start here with a concentration of 1 molarity. It breaks into its ions, but not very much. Only 2 molecules out of every 100 break apart, okay? So I will show you again later in this video, but if you leave this part out, you still get an answer 4 times 10 to the negative 4 instead of 4.08 times 10 to the negative 4, and both will be acceptable, okay? Because it's such a weak acid, we don't worry about the small amount that is broken apart. Okay, now this one, again, another weak acid because the Ka is 10 to the negative 5, so we know it's weak. There's our concentration of acid, and we write out our equation. Because it's an acid, it means it's going to lose its H, it's going to go to the water, form hydronium. We have our Ka, we have concentration of acid, and so you know this is the formula we use. And again, I'm not going to worry about subtracting an unknown X to account for how much of the ions are formed. Because it's a weak acid, it's a very small amount. So I'm just going to leave it as 0.0178 on the bottom. And then I rearrange to get my hydrogen ion, my hydronium ion, and it's asking for the benzoate ion concentration, so that's what I found, because they're the same. It's 1 to 1, 1 to 1. So if I know the H plus, I also know the acetate ion. Now again, if you wanted to, you could have taken away an X here, okay, and you could have solved using a quadratic, etc., but there's no need, okay, at the Chem 12-2 level. All right, so I found this extra practice online, calculating pH and Ka. So here's the example if you just want to screenshot that. So we're talking about a particular acid with a concentration of 0.2 molarity and a pH of 4.88. And they write out the equilibrium expression or equation for you. If you have a pH of 4.88, I'm hoping that you realize you also have your hydrogen ion concentration. Because all they did was take 10 to the negative 4.88, and there's where they got the hydrogen ion concentration. Okay, you have your concentration of acid, 0.2, and so it's simply a matter of plugging in the values. Now, here they're telling you, you start off with an acid of 0.2, you don't know if it's a strong acid or a weak acid. It's relatively weak, you think, because of that pH. If it was strong, it would have a pH of 0 or 1. Okay, so they fill in the ice table. You start at 0.2. It loses as the ions are gaining. So our expression is x squared over 0.2 minus x. That's our equilibrium expression, x squared over 0.2 minus x. Okay, and the x, of course, we found out up here was the value of our hydrogen ion concentration. And how did we find that? By finding the inverse log of 4.88. Okay, so I'll stop here in case you want to screenshot the second part of the question. Okay, and again, you'll see it's a very, very weak acid with a Ka of 10 to the negative 10. So even if you hadn't accounted for that hydrogen ion that breaks off, you still would have had a Ka very close to that. Okay, usually we don't worry about this extra little bit unless we have a concentration, or sorry, a Ka between greater than 10 to the negative 4 and less than 10 to the positive 4. But we've talked about that already. Okay, now this one. This I'm hoping will clarify a lot for you. So try and stay really focused for this question. I'm going to calculate it two different ways. So hopefully you will be able to better envision the difference X could or could not make. So here we're talking about acetic acid. We talk about that acid a lot. Ethanoic acid, that's what's in vinegar. Relatively weak acid. So they're telling us in very small font that the acetic acid concentration is 0.15 molarity and it's 1.086% dissociated. What is the Ka value? So I've written out the expression, the chemical equilibrium expression over here, and instead of using acetic acid, I just used HA, the generic formula. Okay, you could have used CH3COOH, which is what we used over here somewhere. There it is right there. That's the exact equation. So number 12, it's the exact equation. But I just wrote HA over here for simplicity. Okay, so this is how I've set up your credit 3 assignment. I have asked you to fill in blanks for given and then your unknown. So here, 0.15 molarity solution of acetic acid. So what is that 0.150 molarity? What is that called? How do we symbolize that? And I'm hoping that you're telling me that you symbolize that with, there we go, with HA, or concentration of acid. That's what that is. Okay? And then 1.086% dissociated. How do you symbolize that? And I'm hoping you remember that's symbolized by the letter P. What is the Ka? That's what we're looking for. Okay? So I was hoping by doing that, you would see, oh, I have HA, I have P. How are they connected? What can I use those two values for to find? And so when you look on your green sheet, you should see the P and the HA are connected by H plus. So if you use this equation, you'll be able to find the H plus. Now, we're looking for Ka. All right, Well, what formula or equation can I use to find Ka? Well, now that I know H plus, I can find Ka using this equation. Now, this is method 1, this is method 2, and here's how they differ. If I wanted to, I could say I'm starting out with this as a concentration of acid, and it breaks down. How much does it break down? Well, if I know how much hydronium and acetate ions are forming, I know how much HA was lost. Because where is it going? It's being lost to form these two ions. So if I'm starting with 0.15 molarity, and I know that I have formed this much H plus, then that must be what I lost from the 0.15. So you'll note the concentration of my acid started at 0.15, but at equilibrium, it had lost this much to form the H plus. So that's why I have the subtraction on the bottom. Now, I've been telling you, since it's a weak acid, we don't have to worry about that little teeny tiny small number. It's a very small number, not very much of it broke apart. So what I did again over here was the exact same calculations, but in the very last step, I said, let's not worry about that 0.001629 that's forming the H3O plus and A minus. Let's just assume it's so small it doesn't matter. So let's just assume we still have 0.15 molarity acid. If I do that, I get a Ka value of 1.769 times 10 to the negative 5. So I'm hoping you see those are very, very close to one another. So it really doesn't make a big difference if we subtract that little bit or not. And again, either answer I would accept. Okay? All right. Let's just say you were looking at something like this. I chose this question because I wanted to highlight something for you. They give you the Kb. That means this jaspermine is a base, but they're looking for pH. Don't be fooled. Okay, it's going to require an extra step because we're talking about a base. So again, what do you know? You know the Kb, and you also know this 0.2. That 0.2 is the concentration of your base solution. Okay, very important because we're dealing with base. We have to have and talk about hydroxide and weak base. So I have my Kb, they give it to me. This 0.2 is actually the weak base concentration. I can rearrange and solve for hydroxide. And again, I stress that's hydroxide ion concentration. It is not H plus. So once you have that hydroxide, you have to find the negative log of it to get the POH and then subtract that from 14. Okay? Don't assume this is pH. Because we're dealing with a base, when we do all these calculations, we get the POH. Now, some of you might have noticed when you got to this OH minus step, you could have used KW. KW, remember, is 1 times 10 to the negative 14. And the hydroxide concentration is this. So you could have rearranged to find the H plus and then did your negative log of H plus to get your pH. Okay, so up to, choose a color, up to here, this red line and above, everyone should have done the same way. But to find the actual pH, you could have done this or you could have done this, either way. Okay. Now, this question, just a multiple choice, screenshot that. You're going to do that tonight for homework, and then you're going to work on your third assignment for credit, which is due this Friday. Bye for now, grade 12.